Okay, so this week I'll show you something more example about the circuit analysis. And actually there will be a little bit more content than before. And so let's start by the type of source. So first I will just tell you that there are two types of independent source. Independent sources. Okay, so the first one is known as the voltage source. Actually, this is what you have learned before or you are quite familiar with. This is what you should know. Okay, or you can actually regard it as a battery. So in a circuit diagram, we will usually draw it like this. Okay, a circle and with a plus and minus sign. And in this case, suppose we can write it. Sorry, the voltage source is Vs, or in the textbook, it usually use the character E, but I used to using Vs rather than E, but it doesn't really matter. It's just a variable. So in this case, in the circuit symbol, we usually draw it like this, and this minus sign and this plus sign mean the voltage at this node and this node has a voltage difference, Vs, and this terminal is higher than this one. This is what this plus and minus sign mean. And usually for a battery, there will be current going out. Usually, current going out, but not necessarily. So for a voltage source, it really means the voltage difference between the two terminals is fixed, which is Vs. However, the current going out or going in, going out in this figure, if it is going upward, and I'll say going out, the current, whether it's going out or going in, or how large it is, cannot be determined by itself. The current cannot be determined by itself, which means that if you see this Vs in a circuit, if I just put it here, it doesn't connect to anything, then there will be no current. But if it is connected to a resistor, there will be a current going out. And if the resistor becomes smaller, then the current will be larger. Or if it is connected to another voltage source with another polarity, then the current going inside. So we cannot tell it by itself. The current should be determined by the rest of the circuit. The rest of the circuit, or if or we sometimes will draw it in a figure. In the x-axis, we put it the current, and for the y-axis, we put the V, so we call it the VI curve. VI curve. C-U-R-V-E. VI curve. And in this case, the VI curve for a voltage source should be something like this. Okay. So this y-intercept point is Vs, of course, and the current going out or going in can be the current I could be any number, 0 or positive number or even negative number. So in this figure it tells you that Vs is fixed. The y value of this point or the V value is always Vs, but the I can be larger, it can be smaller. It can be either point of it. So according to this graph, we can tell that the slope of this curve is of course 0. The slope is 0, and usually the slope of this curve is nothing but dv di, and we will define it to be the resistance. In the Ohm's law, we know that R equals V over I, but the curve doesn't necessarily to be a straight line. But so sometimes we will define the resistance like this at a point for a curved line. So we can say that the resistance of a voltage source is zero. And thus, if we want to apply the superposition principle, which I'll mention a bit later, we'll turn off some of the sources as we want to. So when the voltage source is turned off, it is short connected. Which means we make the Vs to be 0. So so there's no resistance. So also no yeah. So there will be no resistance, and there will be no voltage drop across it. So this is what you should have known. And the second type, of the independent source is called the second type is called the current source. The current source provides a fixed current. For the voltage source, it provides It provides a fixed voltage. It provides a fixed voltage. But for current source, it provides a fixed current. And in the circuit diagram, we sometimes draw it like this, IS, yeah, something like this, and okay. So contrary to the voltage source, the current for the current source is fixed. However, the voltage across the current source yeah, cannot be determined by itself. Which means that if we just put a current source here, I know that the current is a fixed value, but we don't really know what is the voltage across it. The voltage across it. The voltage across it. And the voltage should be determined by the rest of the circuit. So likewise, we can plot it on the VI curve. We can plot it on the VI curve. So on the VI curve, we can write it like this. We can draw it like this. The current is always IS. However, the voltage can be any value. Can be a zero value, can be positive value, can be negative value. So in this case, we know that the slope of this line is infinity. Is infinity. And we'll say that the resistance of a current source is infinity, is infinite, or is infinite. Okay, so which means that when the current source is turned off, it is open connected. It's just like you connect an infinite resistance across it, then, which means that there is no current can going through that. Otherwise, the voltage is also infinite, which doesn't really make sense. Okay, so after we know the two types of voltage source. One is known as the voltage source. One is known as the voltage source, and another one is known as the current source. We can go into some of the example about the resistive circuit. Okay, so let's see. Okay, so let's so an example like this. Hmm. No. Let's just zoom in a bit. Okay, something like this will be better. So, 2 ohm, 6 ohm, 4 ohm, 5A, 10A, 10A. Okay. Okay. So for this question, find the load voltage. Find the load voltage. Find the load voltage V1 and V2. V1 and V2. Find V1 and V2. Okay. Okay. So in this problem, definitely using the node analysis, maybe a good enough method to solve it. So for node analysis, actually we are writing some equation using the KCL. Using the KCL, this one is actually closely related to this one. The node analysis is closely related to the KCL, and the mesh analysis is closely related to the KVL. Then actually you don't really need to write some equation using KCL and write some other equation using KVL in the same problem. Otherwise, you will write a lot of variable and then you cannot eliminate them. Then you cannot find the answer. So in this case, we use the node analysis. We use the node analysis and write some equation using the KCL. So first of all, we okay. So for the first equation, we try to use the KCL at node 1 at node 1. So actually, there will be 3 current. One is going like this, one is going like this, one is going like this. Actually, you can assume all the current are going in or going out. It doesn't really matter. But, sometimes you can just make everything good enough. Okay. So for this current going in is for sure 5A. 5 is going in, and we assume this current is going out, this one is current is going out. So the current going out should be the first one, this one. This one is V1 minus V2 over 4. V1 minus V2 over 4. And then this one, V1 minus, this is ground, this is 0. So plus V1 over 2. Okay, so very simple. This current equals this current plus this current. And this always tells you that this is an ideal current source. So we don't really know the voltage difference across these two nodes. We need to find the voltage here and here by other things. We only know that the current going through this path is always 5A. Okay, so this is the first equation, and then the second one, we use it here, So for the second one, I suppose this one is going in. So going in is 10A, and I assume this is going out, this is going out, this is going out. You may find that, I assume it is going this way here and going another way here, but it doesn't really matter, because if I assume for this case, if I assume the current going in this way, then for this current it will be V2 minus V1 over 4. And for that one, if I assume that going that way, then it will be V1 minus V2 over 4. And it's actually the same stuff. Because if I just assume this current to be in this way, then this term should be on the left hand side. It will become V1 minus V2 over 4. So it turns out to be the same equation. I just move this term to the left hand side, which doesn't influence the equation itself. So when you try to write an equation, you keep in mind that for this case, what I want to know is this current going out, then I know that it should be this voltage minus this voltage all over this resistance. Then that's enough. So there are still two more current going out. One is this. So we have So we have plus 5 for this current going upward, and also this current going downward, which is V2 over 6, V2 minus 0 over 6. This is ground. So very simple. So we have two equations, and with two unknown. V1 and V2 are the unknown, and we have two equations. So actually we can, of course we can solve it. As long as you should have learned how to solve this equation in high school. So actually, for the first equation, we multiply both sides by 4. So we have 20 equals V1 minus V2 plus 2V1. So it will become 3V1 plus, minus V2. So this is 1 multiplied by 4. So for the second one, we can multiply both sides by 12. So on the left hand side, it is and before doing that, we can just move this 5 to the left hand side, which become minus 5. So these two terms become 5. Okay, so to simplify a little bit, so 5 times 12 is 60 equals 3V2 minus 3V1, and then plus 2V2. So it becomes well, minus 3v1 plus 5v2. Okay, so we add the two equations together. We add them together. So 3v1 and minus 3v1 are cancelled. And then these two add together. It becomes 4v2. And then on the left hand side, it is 80. So V2 is 20 volts. So finally, we can just using this one, so that V2 should be equals to 3V1 minus 20. Okay. No, not this way. Not this way. Okay, so we should find V1. We should find V1. So we move V1 to the left hand side. So it is V1 plus 20, and then over 3. V2 plus 20. V2 plus 20. So we have V2 plus 20, and then over 3 should be equals to V1. Okay, so V1 will be nothing but 20 plus 20 over 3. So 40 over 3 is 13.3 volts. So finally, we know that V1 is 13.3 volt and V2 is 20 volt. And actually, if you are not familiar with it enough, I try to So finally, we know that V1 is 13.3 volt. So here we have 13.3 volts, and maybe I can erase some of the green boxes so that it will not be so messy. Okay, something like this. Okay. Well, so this should be like this. So this is 13.3 volt. So this would be 20 volts. Okay, so in this case, we should be able to know that for this current, it should be 13.3 minus 0 over 2. So it will be 6.7 something 8. 6.7. And this current is of course 5A. And for this one, it should be 20 minus 13.3, which is 6.7 over 4. 6.7 over 4, which is about 1.78. So in this case, 5A going in this node, 1.7A going in this node, and 6.7A going out from this node. So which matches the KCL. So in this case, for this node, we know that 5A is going in this direction, and likewise, 1.7A going to the left-hand side, and for this current, 10A is going upward, and for this branch, the current will be 20 volt over 6, which is 3.38. So for this node, the current going in should be 10A, okay, and the current going out should be 5 plus 3.3 plus 1.7. So it also matches the KCL for this one. 5 plus 1.7 equals 6.78. So this is going in, this is going out, this is going in, this is going out. They should all agree to the KCL as long as the calculation is correct. Okay. So let's see another example. Okay. Okay. So the next one, it will be something like this. 10 ohm plus 2 volts, 2 ohm, 2A, 4 ohm, 7A. Okay, something like this. So find the node voltage also. Okay, so find V1 and find V2. So this question asks you to find the node voltage. Which means to find V1 and V2. The node voltage is two V1 and V2. Okay, so in this question, if you just assume it is something like the previous one, then you will face some problem, because as long as if you try to write the node, the KCL at this node, actually you should be able to know the current going this way should be 2A, no problem. The current going in this way should be V1 over 2 ohm, no problem. The current going in this path should be V1 minus V2 over 10 ohm, no problem. However, this current, you should not be able to write out this current. You should not be able to write out this current. You can only find the current going this path after you have solved the the, the, the circuit, and you are not able to write the current going this path with a simple equation. That's uh, uh, does not be the case for this one. So if you want to use the KCL with a voltage source, there will be some tricky step. Suppose this is the troublesome part. It is a voltage source. We don't know the current. So and then this node and this node is connecting to this voltage source. So we just assume this to be a big node. We call it a supernode. The reason why we can do that is something like we are able to know the current. For example, this may be called I1, I2, I3, and this is the current going through the source. We call it IS, something like this, and maybe we can call this one I4, I5. Okay, so for the left-hand side node, I1 is going inside node 1, and I2, I3, and also IS are going outside. So we can write like this. Of course, we can write the expression of I1, I2, and I3, but we are not able to write out IS. And for the right-hand side node, IS is going inside. Also, I2 is also going inside. And and actually I4 and I5 are going outside. This is S, not 5. This is also S. So when we add them together, for on the left hand side, which will become I1 plus I2 plus IS. On the right hand side, we have I3. This should be I3. This should be I3. So on the right hand side, it should be I3 plus I4 plus I5 plus IS. So IS and IS can be cancelled. And well, I forgot the term I2 plus I2. And actually I2 and I2 can be cancelled. So finally, we have I1 equals to I3 plus I4 plus I5. Something like this. The point we can use the supernode is that we assume this is a very big node, so we consider all the current going in this big node. The current inside it, we just ignore it because it is already inside, so it doesn't really matter. So when we consider all the current going in or going out, this supernode, we know that I1 is going in, so it is on the left side. I2 One is going out, one is going in, so no problem. So we can just cancel it, just like we cancel it here. And I3 going out, so put it on the right hand side. I4 going out, I5 going out. So we put I4 and I5 on the right hand side. And we will return out, get the same equation, so that we don't really need to write an equation at this node and write another equation at this node and then add them together. Actually, we can regard this is actually a big node called the supernode, or actually you can draw the box. Draw the box a little bit larger. You can draw this box a little bit larger like this, because actually this 10 ohm resistor is parallel with this one. So the resistor connect to the same point here. So the current going in this path and that path always cancel for that supernode. And in this case, we only need to care about I1, I3, I4, and I5. Then we can write the node equation. We can write the node equation. So in this case, we can write the node equation like this. So for I1 is nothing but 2A. I1 is nothing but 2. And for I3, V1 over 2. V1 over 2. And for I4, V2, no, actually 7. And for this one is I5, should be V2 over 4. So we get an equation according to that correspond to this supernode. We got one equation but with two unknown. Where is another equation so that we can solve it? Actually, another equation lie in this supernode, which means that we know that this is a current source. This is a voltage source, which means that the voltage difference between these two nodes is fixed, which means that we know that V2 minus V1 should be 2. So we have two equations with two unknown in this case. So actually we can simply move it like this. V2 equals V1 plus 2. We just move V1 to the right hand side and then we substitute in the first equation. And then we move these two to the right hand side so that 0 equals V1 over 2 plus 5, because it is 7 minus 2. And then we have V2, which is V1 plus 2. V1 plus 2 over 4. Okay, so we multiply both sides by 4. So it will become 2V1 plus 5 plus V1 plus 2. So 2V1, V1 is 3V1 plus 7. Oh, sorry, I forgot to multiply. This one by 4. So this one should be 20. This one should be 20. So this one should be 22. This one should be 22. And in this case, V1 should be minus 22 over 3, which is minus 7.333 volt. And for V2, we can use this equation, so that which is V1 plus 2. So it will become minus 7.33 plus 2, which is minus 5.33 volt. So finally, we got the no voltage, V1 and V2. And likewise, you can double check all the current going in or going out a node should be correct. Should match the KCL. And in this case, after you know what V1 and V2 is, then you'll be able to find what is IS. Actually, we can try to find IS like this. Let's see. Okay, we put it here. So just now we know that, let's say, we know that I1 for the left hand side node, we know that I1 should be equals to I2 plus I3 plus IS, which means that IS should be equal to I2 plus I3 minus I1. So for I2, it should be V1 minus V2, which is minus 2 volt, over 10, minus 2 volt over 10. And yeah, and for I3, which will be V1 over 2, which is minus 7.33 over 2. And I1 is nothing but 2A, so minus 2. So this is minus 0.2 minus this is 3.66, something like this, 3.667, and minus 2. So finally, we will get IS should be minus 5.86 A, which means actually the current here should be something like this. This is 5.86 A, going that way, which means actually the current is going inside the voltage source. Usually when you just connected a voltage source to a resistor, suppose it is Vs, then the current should be going like this. Then IS should be VS over R. Suppose VS is positive, R is positive, then IS is positive, which is this way is going outside, but here for this case it's going outside because these two are stronger than that one. Then actually this voltage source consume power rather than providing power. Okay, so let's have a break here.